Hello guys, hope you're doing well. My name is Mahmoud Kiasri and welcome to the new chapter of electrical circuit. So at this chapter we are going to talk about two important laws that we had, which was KCL, Kirchhoff's current law, and KVL, Kirchhoff's voltage law. We are going to talk about it in detail, that actually what's going on inside of that. We've been using them for a long time in this course, but we haven't dedicated any specific subject to that area. So at this point, we are going to talk about it. So the foundation of circuit analysis, everything we know about circuit analysis comes from two simple laws. The KVL and KCL that comes out from this guy. Two laws, infinite circuits. So this is a little bit biographical detail about the Gustav Kirchhoff, actually the guy, an important one. It's behind the scene of these two important formulas. So its contribution for the electrical circuit, actually his laws provided the first one-dimensional framework in order to analyze electrical network. They are derived directly from the conservation principles. Energy and charge, the two simple things we know, and we got these two laws out of them. So remarkably, they remain unchanged and are going to be foundation of all modern circuit analysis. So let's see what are them related to the big picture, then we can talk about it in the detail. So the two pillars of circuit analysis. The very first thing is that why they matter, why we do care about them a lot. Because they allow for the analysis of any circuit, regardless of the complexity. And they also provide a rigorous mathematical foundation for advanced technique like mesh and nodal analysis, that we are going to touch them. Actually, we're talking about one of the theorem, if you remember, superposition a little bit, but then we are going to talk in detail about other positions or other kind of characteristic related to other theorems that are going to help us in order to handle any complicated circuit. So the Kirchhoff's voltage law. So let's talk about these two pillars of circuit analysis. As we just mentioned, they're going to be important because of these reasons, and then we are going to talk about each of them in detail. The KVL, Kirchhoff's voltage law, what would it say? It says that you can apply it for each loop. The very first important thing about each electrical circuit theorem or any kind of analysis would be about some terminology. So the very first thing that related to the terminology is loop. What is that? Loop is any closed path in a circuit. Imagine that you do have a circuit like this. This is going to be your source, whatever is V, and you have another R. This closed path is considered as loop. You can have different kind of loop. Obviously, at this point, you only have one loop, and imagine that you have another R over here. So you do have another loop, the second loop, and you have the main loop, which would be the third loop itself. So this one is going to be based on conservation of energy. And the rule over here is that sum of voltage rises equals to sum of voltage drops. It means that whatever voltage rise that you have because of the voltage source, because this guy is the energy, this guy is going to give energy to all of the electrons and is going to boost up your current. This is about the raising voltage. On another hand, we do have resistance. Those guys are going to consume voltage, or we do have some voltage drop there. Some kind of equation or this law is simple. The amount of raise that you have because of your source is going to be as the same as accumulation of all of your drops that you had because of your other resistance. What about the KVL? KVL is a little bit simpler. It says that this one, the very first thing that you have to know, this one is going to be applied for the nodes. We talked about nodes means that junctions where wire meet. At this point, I do have different kind of wire components connected at the same or at a common spot, so we call it as node. So this guy is based on the conservation of charge, and it says that the total entering of the current that goes inside a node is the same as the total current leaving it. Imagine that I do have my currents that gets inside and some currents gets out. The accumulation of all of these guys are going to be the same as these guys, right? Let's talk about the Kirchhoff's law a little bit in detail. We mentioned a couple of things, and the statement is this. The algebraic sum of voltages, by the way, why we are talking about algebraic? Because some of the voltages could be positive, some of them could be negative. Around any closed loop, we do have a closed loop, we talked about it as loop and a closed loop, in a circuit equals to 0. What does it say? It says that if you sigma V loop, if you add all of those voltages based on the fact that some of them are positive, and some of them are going to be negative, or we do have voltage drop. If you add all of them, they would be 0, and can also be expressed as the voltage of sources at some points is going to be equal to voltage drops. Or expanded form is this: V1 plus V2 plus V3 plus whatever component that you have plus Vn is going to be 0 itself. Here's the physical basics, the conservation of energy. The net change in potential energy after going to be traversing a closed path and returning to the start must be zero. It means that you do have the energy, and my energy is going to boost up right now. Then because of all of these two guys, because of all of these resistors, my energy should go down till the fact that my energy should reach to zero. Then again, I do have this loop and it's going to boost up. This is the fact about the KVL itself. What about the sign convention? This is some kind of agreement that we have related to that. And it says any place that you had voltage raises, it means that you're moving from negative to positive. It's most commonly related to the source itself. You're going to treat that guy as a positive voltage. Whenever you have voltage drop, moving positive to negative, which is related to resistances, you're going to treat them as negative. So here are the 6 steps that actually we can use in order to make sure that the KVL you're using is going to be okay. The very thing is about identification of closed loop. Again, we were talking about the closed loop. Not all the time we only have one. Sometimes we have more than that. So again, a loop is any path that returns to its starting. Any closed path at start that reach to its starting. And a circuit can have multiple loops. As I just told you, you can have 1, 2, 3, or more than that. Another thing would be about the direction. Select either a clockwise or counterclockwise path. It is important for you guys in that you're choosing which path for the direction of your current. At the final step, it doesn't matter which direction you use. The only thing that could change is the sign. But it would be better to at least have a ground basis at the very beginning. So the choice is arbitrary. You can do it whatever you want, but consistency is critical. If you have one direction, try to consider it for all of the loops. Then we do have the trace the loop and note voltages. As you move along your chosen path, whatever your path is, identify every voltage source and voltage drop across resistors, marked there as positive and negative. We know that. The voltage, even is increasing, considered as positive, and when voltage is decreasing, considered as negative. Another thing that we have to know is, as I told you, the current in voltage source goes from negative to positive. So we do have a negative positive for the source and gets inside the positive side of resistor and gets out of negative. This is somehow, it's not going to be the fact that you have to do it. It's not mandatory, it's arbitrary, but it is better to use this way because at the end you're going to have a better life. Step number 4 is that apply the sign conversion. And when moving from negative to positive through a component, it's a voltage rise. As we are moving from negative to positive, it means that when we are moving through our source, we are going to have the rise up in voltage itself. And when moving from positive to negative through a component, it's actually a voltage drop because of resistor. And we can write down the equation as we had related to some kind of the KVL. The sigma of all of the rises subtracted by sigma all of the drops is going to be 0. And finally, we can solve it for the unknowns. So let's see an example. Let's see a very basic example. So at this point, I'm looking for the current that flows inside this circuit. The very first thing is that you can obviously find I based on the simple fact that it's going to be V divided by R total. It's going to be 24 divided by 3 plus 5, 8 plus 4, 12, and it's going to be 2 amp. This is one way. But we are going to use the KVL itself, and we are going to use those steps in order to see that how we can do that. So let's apply this KVL clockwise. It means that current moves from negative to positive. I do have positive and negative for my resistors like this. Let's apply the current and let's see what would happen. So through the battery, I do have a 24 volt of rise. It means that my energy is going to boost up, so I do have rise. I do have drop of 3 times I, 5 times I, and 4 times I. Why resistance times I? Because we know it. We are talking with about the voltage, so we have to use the Ohm's law. Is that the case? So then we are going to write down the KVL equation. The KVL equation say that the algebraic accumulation of all of the voltages due to the rise and drop should be 0. 24 is the rise because of the source. 3y is drop. Now 5y is drop. 4y is drop. And if I do have that, if I rearrange it, my I is going to be 2. If you would like to verify that, you can use the law that we already know about the Ohm's law and compare it with this, and you can see everything is okay. So what would happen at this point if rather than only one source, I do have 2 sources? It's still I can find the final question or the final goal is to find the current or the total current. if I would like to find that, I have to use the superposition. You guys know about the superposition. Superposition means that when you do have more than one source, two sources or three sources, you can do it step by step. Consider one step as 0. It could be a voltage source or current source. When you consider that 0, it means that either a short circuit or open circuit. Then find that the specific value could be current or voltage based on only one source, and then stop that specific source that you had, move to the next source. Still do the same concept or the same procedure that you did from the last one and move it forward. After that, try to decide about the direction. If all of them were aligned with each other, you have to add them up. If they have some problem, you can subtract or some kind of do anything that you like. But at the end of the day, this is going to be one of the theorem that we were talking about it, and we do have one video related to that. So at this point, we are going to use the KVL. How we can do that? Let's see. I do have 12 volts, I do have 2 ohm, I do have 3 ohm, and I do have 1 ohm, and I do have another voltage source. The very first thing that I would like to say is that obviously when the current goes this way, the current is going to be what? It's going to be divided into two parts. One could be this, and another one could be this. If I would like to open up that area, if I want to open up that door, it could be a little bit challenging. Why? Because right now I do have a better way to use that. I do have a way that I know the voltage drop because of this guy actually was how much? Was actually 6 volt itself. Is that the case? Because the voltage of this guy is the same as voltage of this guy. This guy is producing, this guy is consuming. So I can say that the voltage drop because of this 3 ohm was actually 6 volt. How I can use that? I'm going to have my I over here. I don't care about the I over here, but I also do have the I over here. I can write down the KVL. So what did it say? The KVL equation, 12 volts, which is going to be rise, subtracted by 2I, which is going to be what? Because of this resistor, subtracted by 3I is going to be what? Because of, then I do have this subtraction by 6, and this 3I actually, to be honest, it's extra. Shouldn't consider that. Cool. Then I do have my subtracted by 1y because of the voltage drop over here. If I do this calculation, what do I have? I do have 6 subtracted by 3I is equals to 0. So my I should be 2 amp itself. So this is completely wrong because of the fact that I forgot when I use this 6 voltage, actually I somehow get rid of this 3. But by using the 3I again, I'm changing everything. So my I is going to be 2 amp. So how I can find it or how I can prove that guy is that my 12 volt should be equals to 2 times 2, which is going to be 4 volts, plus 6, plus 2. Finally, I do have my value that I would like, as simple as that. So guys, again, be very, very careful. I did something wrong and you guys have to know it, that why I did wrong. When we were talking about the whole circuit over here, let me just get rid of that. When we were talking about the whole circuit, I told you that this R2S3 is going to make me some problem. Instead of getting rid of that and instead of just working as current that goes this way, for example, I1, because obviously I is going to be divided at this point, I somehow suggested that I can say I do have all of the voltage that I have over here. I know for a fact that R2 is going to have a voltage drop, right? The voltage drop over R2 is the same as voltage rise in V2 but with flipping sign. So I do have R2 as -6. So I'm going to use that. But the one that I was calculating it, I also considered the 3y over here. That's why I had the wrong number. By changing that, I do have the right number. So this problem, again, it could happen to anyone. That's a genuine problem. So try to be careful not to have it in your work by practicing more. So KVL versatility. Finding an unknown voltage. So what would happen if I would like to find an unknown voltage? Again, this is so simple. So I do have a 36 volts. I do have V1 as 8 volt. Whatever component is that. V2 is 12. And I don't know what about this, but V is 10. So I can use the KVL. It says that 36 is equal to the accumulation of all of the voltage drops, right? So I do have 8, 12, and 10. So this guy is going to be 6. Or I can write it down as like this. E or sigma of voltage loop is going to be 0. 36 subtracted by 8 by 12 by V3 by 10 is equal to 0. I can find the V3 as 6. This is one of the most simple questions that we have. So the second pillar, the Kirchhoff's current law. Let's talk about it. What does it say? It says the algebraic sum of all currents. Again, when we are talking about algebraic sum, it means that some of the currents has the sign of positive and some of them has the sign of negative. All currents entering a net node equals the algebraic sum of all currents leaving the node. Or imagine that I do have different kind of current that gets in. I do have I1, I2, and I3 gets in, I4 and I5 gets out. The accumulation of all of these three, if I assume that the sign is going to be positive for all of them, is going to be as the same as the accumulation of all of these, if I assume that the sign is still going to be positive for them. Or I do have sigma of I in is equal to sigma of I out. Can also be expressed as sigma I node. At this point, I have to consider a specific sign for each of those guys as entering or are going to moving out. So the physical basis says about something related to conservation of charge. The charge cannot be created or destroyed, nor can it accumulate at a single point or node in a steady state circuit. What flows in must flow out. Whatever current gets in should go out. So this is some kind of a ground rule that we are going to have in order to make sure we are talking about the same language. So the currents that entering a node are going to be treated as positive. I1, I2, and I3 are going to be treated as positive, and the current gets out or leaving or should be treated as negative itself. So the KCL method, obviously it has some step. So the very first thing you have to do is identifying a node. A node is the place that you do have three or more wires or components are connected to each other. It's a junction, right? Then you have to label all of those currents. It's the I1, I2, I3, whatever you like, doesn't matter. At this point, you have to draw arrows on each branch connected to the node to indicate the direction of the current flow. And if you're unsure, you can just assume the direction. It doesn't matter. The math at the end will correct you. And choose a sign convention. Again, we decided that the common choice is the current gets in are positive and the current gets out are going to be considered as negative. Write down the KCL equation. Whatever equation that you have, either you can just write it down on the top side or the bottom side, and you can find a number and solve the unknown current. Whatever current that you need, you can find it. Imagine that we do have a concept like this. In my circuit, the I1 is 5 amp. It gets in. I2 is 2 amp, and I'm looking for I3. So based on the two ways, either the first method or the second method, I can find my I. Obviously, I3 is going to be the same as I2 and I1. Why? Because these two guys are positive, because get in, and this guy gets out, so this guy considered as negative itself. So another problem. You have I1 as 8, you have I3 as 3. I don't know I2 and I4. It means that I have two unknowns. But at the same time, I know something. That I2 is going to be 2 times I4, or I2 is twice the value of I4. How I can do that? Still the same. I do have something like this. I1 plus I3 is going to be I2 plus I4. 8 plus 3 is going to be I2 plus I4. I know something about I2 is going to be 2I4. So 11 amp is going to be I2 plus I4, or 11 is going to be 2I4 plus I4. If you do the calculation, you do have your I4 and you do have your I2. As simple as that. You can also prove it. If you compare I1 plus I3, it should be the same as I2 plus I4 itself. So at this part, we were talking about the KVL and KCL, two important laws that we touched those, but we haven't talked about them in detail. At this point, we talked about them, what was the definition, how we can use them, and finally, we are going to solve a question. So this question could be a little bit challenging because it contains so many equations and so many different concepts, but just in case you can be my guest, try to think about this question by yourself, try to solve it by yourself. At this point in this video, we're going to do that together step by step to make sure that you guys completely understand it. Let's move on. So, as I promised, let's talk about it. The very first thing we have to do is just labeling, obviously. By labeling a currents, that we already did at this point, and then we have to show or declare the position or the polarity of the voltages. So I do have this one as positive and negative, positive. Cool. So then we are going to do what? We are going to use another color at this point. And let's see what the question asks. Write KCL equations for the two main nodes. So we are looking at two cases, means that this guy, node A and node B. So case for node A is going to be what? Is going to be I1 plus let me just do it like this. That would be way better. Cool. This is going to be my I1. This is going to be current that I don't know, but this is the current that I know. So I can say I1 is going to be equal to, I don't know about that. For example, I call it as I12 plus I2. This is the first KCL. Then I do have the second KCL at point B, KCL of B. What did it say? It says, I have it as I2. This is the current that I don't know, I23, and this is the current that I know, I3. The second KCL says that
I2 equals to I23 plus I3. As simple as that. So that was the first one. Write the 3 KVL mesh equations. The 3 KVL ones. We do have that for I1, I2, and I3. So the KVL for the first loop, by the way, the first loop is this, second loop, and the third loop. Is that so? So let's talk about it. So at this point, very first KVL is what? We know the voltage source is the source of voltage rising. So I know 36 equals to voltage drop over R1, 3 times I1. Voltage drop over R2, 6 times I12. The next KCL, the next some kind of KVL. The next KVL is all about the voltage drop. So I can say that I consider one of these guys, this is a very important part. I consider one of these guys as my hypothetical source, like this one, and consider these two guys as my voltage drop. So at this point, for the second KCL, what do I have? I do have 6 times I12 equals to 4 times I2, then plus what? Plus 4 times I23. Then for the final KCL, I'm going to do the same concept that I did. At this point, I'm going to, let me just get rid of all of that. At this point, I'm going to consider my R3 as my source, and is going to consider that one as my source, or I can do it with 24 volt. It doesn't matter, whatever you're doing. So at this point, for the KCL number 3, I can say that I can use another way. And my way is going to be like that. Let me use another color. My way is going to be like this. If I'm moving toward this place, if I'm moving toward this part, I have to move from this point, move, and then move back to this point. At this condition, I'm going to give you a new way. New way which says that let's start from this point. If I do that, I do have what? Based on all of those positive and negative things that I had. I do have negative of voltage over voltage of R3, which is obviously going to be considered as what? Is going to be, at this point, voltage drop. This guy is going to be 4 times R23. I'm going to same direction. Then I have to move to this side. So at this point, I do have what? Plus, because of the sign of R4, 2 times I3. Then I do have the plus sign for voltage, plus 24 volt, plus 8 times I3 is equals to 0. So at this point, I somehow use another format of the KVL, and it says that instead of just using the way that we had, we can use a way that somehow it was mentioned at the very beginning of the point. If you remember, a closed loop means that you have to start from one point and end through that specific point. So by using that, I wrote down my third KCL. Probably I'm going to make more videos related to KVL and KCL. It is so important, especially about this kind of circuit, so don't worry about it. So solve all 3 mesh currents. Right now, I have to use these guys, use these 3 as my equation and solve them in order to find all of the currents. I12 and other kind of currents. But one thing we can do before that, because as you can see, I do have a little bit of more unknown rather than just equation themselves. I do have I1, I do have I2, I do have I3, I do have I12, I23, and another I23, and another I3, and I12. So it's a little bit high. I do have 3 equations, but I do have 5 unknowns. How I can get rid of that? As you can see over here, I12 equals to what? If I do it backward, it is equals to I1 subtracted by I2. I23 equals to I2 subtracted by I3. By adding this inside of this one, I can change my equations themselves. As simple as that.